I learned yesterday that I can give this talk in English. That was good news for me. I hope you can understand me. So it's a pleasure to be back here in CCA. Since 2003, when I was here for 5 months. I've been here, I think, 2 or 3 times, but it's always nice to come back and see my friends here. Okay, so here's what I'm going to do today. I'm going to tell you about atmospheric trajectory models, which is the main type of Lagrangian model that I use. I'm going to show you some examples of how they can be used to support air pollution studies, and also I'm going to give a more detailed talk about a particular project where we used Lagrangian models to create an improved model to estimate concentrations of fine particulates. And I'm also going to show you some pictures of the Green Bay Packers, my favorite football team. I learned a few years ago, actually back in 2003, that a lot of Mexican people are interested in American football. I was surprised about that. But I also learned that everybody's favorite team is the Dallas Cowboys. Yeah. That's our enemy, you know, for Green Bay. Okay, so let's go. So air trajectory models. These form the core, the internal structure of most Lagrangian models. So an atmospheric trajectory model is very simple. The mathematical formulation is very simple. The position, three-dimensional in space, position is an integral of the wind field. So it's very simple. I think of it as the wet finger technique. So the wind is from the west at 10 kilometers per hour, right? So I go 10 kilometers, and then the next hour, what is the wind? The wind is from the south, you know, I go this way. Okay, that's a trajectory model. And the numerical formulation, the numerical solutions to the integral are a little bit more accurate than this. I just show these to demonstrate that it's a very basic, simple model. Now, there are not very many atmospheric trajectory models in the world that people use. Now there's High Split, and there's a European one called Flexstra, and the Japanese Meteorological Service have another one. The reason that there are not very many trajectory models is not because the models are complicated. They are not complicated. It's because managing the data is complicated. When you use a trajectory model, you want to ask a question, you know, where the air that's here now, where was that air 1 day earlier, 2 days earlier? So you need to have meteorological data for everywhere. The whole world, three-dimensionally, all the altitudes, and not only winds, also temperature and other variables. So that's the reason why there exists only a few trajectory models. I used to manage one trajectory model, and I gave it up after 5 years because managing the data is an enormous task. Okay, so there's 2 types of trajectory models, forward and backward. So this is an example of a forward trajectory model. So the equation is solved here. Actually, I'm supposed to stand here, I forgot. The equation is solved, so the final position is equal to the initial position plus the wind speed at that initial position times a time increment. And then again, as many times as you need. So here's a result. So this is one particular trajectory that I calculated just to demonstrate. It starts in Monterrey, Mexico, and it shows that the air moves in this direction. Okay, and here something strange happens with the winds, so it does this, and okay. Now the atmosphere is three-dimensional. Winds are three-dimensional. So this is a two-dimensional representation. Here's the third dimension. So this trajectory, just a sample, was programmed to begin at 500 meters above the ground. So as it moves towards the southwest, it rises a little bit and then it sinks. And okay, so you have the vertical component and the horizontal component. Now, this is a backward trajectory, so it's the same model except we use a minus instead of plus. Okay, so that's like this. I go backwards. Okay, like that. Okay, it's the same concept. So here is a backward back trajectory for Monterey, and it shows that on this particular day, the air that was sampled or the air that existed in Monterey came in this direction along that path. Okay, and this is the again the vertical component. So this horizontal coordinate here in southern Mexico corresponds to this point. So as it moved north, vertically it followed this path. Very nice, right? The models, very useful. Forward trajectories, they can tell you if you have a pollution source, you want to know where will the pollution go. Forward trajectories are an excellent tool for that. Backward trajectories, you have an air sample and you want to know where the air came from. If you have contaminants, you might want to know what are the likely sources of those contaminants. So backward trajectory models can tell you that. But as I wrote here, these models are very dangerous because it is very easy to interpret them incorrectly. So here, for example, is a line on a map. Oh, on this day, the air in Monterey came from here. You know? Okay, finished. Okay. A trajectory model is only an estimate. Also, there are a lot of uncertainties in the estimate. Another thing to remember is you can think of the trajectory here as an estimate of the path of an air parcel. So in meteorology, we have this concept of an air parcel, which is a small unit of air. I like to think about it as a balloon without the skin. Okay? A small unit of air that moves along and it retains its properties except pressure. Okay, it accepts the environmental pressure of wherever it goes, but its mass properties like pollutants and water vapor and so on are retained, and its temperature can change adiabatically, for example, but other than that, it's retained. Okay, so the trajectory model represents the movement of a small parcel of air. But in addition to that, you have diffusion. And diffusion is not represented in these models, at least not in this form. Okay? So maybe the air that was sampled here came from here, but maybe also it came from some other places. Okay. So here's a technique that can be used to evaluate the uncertainties. So I told you that the models are dangerous, and the danger is you can make an interpretation that's not terribly intelligent if you are not careful. So this is a simple method to be smart with trajectories. So let me show you. In this case, we have a weather map. Sea level pressures, winds for the United States and part of Mexico. So suppose that we wanted to calculate a trajectory. In this example, I'm going to use forward trajectories, but the concept is the same for backward trajectories. Suppose we were interested in the forward trajectories from two locations, one right here off the coast of Baja California, and another one here in the western part of Wisconsin. I live right here on Lake Michigan. Okay. Okay, so the technique we use is we create a grid. I don't know if you can see the purple, but the middle point is the location of interest. So for example, this point could be this point. And then we create a grid of points. It doesn't really matter how many points you use. I like to use 9. The spacing is arbitrary. I like to use this value because it represents the distance corresponding to 1 degree of latitude. Okay, so you calculate the trajectories not only from the point of interest, but also from the other points. So for Baja California, in this particular case, it looks like this. All of the trajectories look exactly the same. Okay, so that indicates that the meteorology is uncomplicated. And that means that you can have confidence in the trajectory. Now, you're only interested in one, the one corresponding to the middle point. Okay? But you need the other ones to determine if you can have confidence in the trajectory model results. Now, here you have a different story. The location of interest is in the middle of a weak low pressure system, and the trajectories from these 9 points centered here are very different. So the trajectory corresponding to the point of interest, I think, is this one. So you might conclude that the air that was here is going to follow this path. But if you begin the calculation only a little bit farther to the north, the air takes a very different path. So in this case, you can conclude that you cannot have confidence in the trajectory estimate. So that's the way to use, to remove the danger of trajectory models. Okay. Here's a couple of examples of how single trajectories can be used to help interpret air quality studies. So in this case, the group here, the Contaminación Ambiental group, had some samples of atmospheric deposition in Veracruz. So they were interested in estimating the source regions of the contaminants that they measured. So in this case, I did the same thing. I calculated the trajectories for a grid of points. These are, in this case, it's back trajectories. So the air is moving in this direction. And all of the trajectories look more or less the same. Again, indicating that the meteorology is uncomplicated and you can put confidence in the trajectories. Okay, so that's good. So we can conclude in this case, for example, that the contaminants in the rain may have come, I don't know, from part of Cuba or the Yucatan Peninsula, or more likely the oil platforms in the Gulf of Mexico. Now here's another one corresponding to a different pollution sample on a different day, and the grid of trajectories has a lot of dispersion. So in this case, we cannot say with confidence where the material came from. Here's the Green Bay Packers, your favorite team. Okay. So trajectories can also be used in a climatological sense. So they can be used, like I showed you, to support air quality studies sample by sample. But they are also useful in determining climatological features of atmospheric transport. So I'm going to show you a couple of ways that the models can be used in this way. So in this case, again, in conjunction with Rodolfo Sosa and the Contaminación Ambiental group here, they had a project at the archaeological site El Tajín in the northern part of Veracruz state, and they were measuring acid deposition and some other things, I think. I don't remember. So here what we did is, for a period of 5 years, we calculated one trajectory per day. And we are plotting them by month. So December, January, February, etc. So here you have 5 years worth of Decembers, 5 Decembers, one trajectory per day, 5 Januaries, etc. So what we can see from the trajectory is, it's very clear actually, that there are 2 transport regimes. There's this pattern here, where winds from the east. Okay, these are back trajectories. They all arrive at the same point. So one regime is the easterly flow here. That regime is present all year. Every month has more or less half of the trajectories are from that regime. And in the summer months, June, July, August, trajectories are exclusively along that path from the east. Now, in the other months of the year, you have this path from the north, from the northwest. So in the winter, for example, that corresponds to when the air is cold. I have to say cold because I'm from Wisconsin where the air is really cold. Cold fronts, okay, storms. Okay, so now remember the equation for trajectory models. It involves an integral. So trajectories are, in a very real sense, they are integrated meteorology. Okay, so you take the weather conditions over several days and they combine in a continuous way like an integral to give you something, to give you these patterns. But it's meteorology that's causing the patterns. It's not the trajectory model, it's the meteorology. So there's a reason that the patterns look like this. So here, for example, is average sea level pressure fields for winter and for summer. So here's Mexico, right? This is the site in Veracruz where all the trajectories arrived. So over here you have a large subtropical anticyclone with air circulating like this, and on the bottom half that brings the air like this. They call this anticyclone a semi-permanent feature, which means it's always there. Okay, so that accounts for the constancy of the easterly winds during the summer. During the winter, you have the semi-permanent high pressure system, but it has moved, in the winter it moves farther away from the coast. So you still have the circulation that brings the easterly winds here, but because it's farther, it allows the northerly winds from North America to penetrate into Mexico. Okay, so this is just to show you that the trajectory models really do represent integrated meteorology. Okay. So something like this we call trajectory climatology. And it's very good to answer basic questions about atmospheric transport. For example, there's corrosion on this beautiful pyramid due to air pollution. Where's the air pollution coming from? Well, maybe people might think, oh, Mexico City, because Mexico City has all the pollution sources. But no, the air never goes from Mexico City to there, and the trajectories show that very clearly. Okay. Okay, now remember that the winds are three-dimensional. So when the air is moving from the east or from the north to Veracruz, it might be moving up and down as well. So the trajectory models can give us information about this, and this information is useful for estimating the sources of the contaminants that are measured. So in this graph we have the months here, and this is altitude. Well, I'm a meteorologist, I always think about pressure rather than altitude, but essentially it is altitude. And these bars represent 1 day upwind, and then 2 days upwind, 3 days upwind, etc. So remember, in June, July, and August, the winds were exclusively from the east. the altitude of the air as the trajectories are bringing the air to Veracruz is between about 980 and 900 hectopascals. So that's between about 200 meters and 1 kilometer. So it's in the boundary layer, the capa limite, exclusively. So that means that there is a very good likelihood that pollution sources, which are almost entirely located at ground level, can contribute to the contaminants that are measured in Veracruz. Now, in the other months of the year, remember that you have two kinds of transport, from the east and from the north. Now, for those months, the average pressure is a lot lower, which means the average altitude that the air is moving at is higher. So what that tells you is that pollutants that come from those areas, from the north, for example, are more diluted because there is a larger volume of air over which they mix. Okay, so there are contributions from sources to the north, but the contributions are smaller in magnitude than the contributions from the sources to the east. And that's the altitudes tell us that. Okay. I think it's time for some more Green Bay Packers. Do you like the snow? Okay. It's like when you are tasting wine, you have to clean the palate, right? So, cleaning the palate. Okay, there's another method of Lagrangian modeling where trajectories can be used to determine transport climatologies. That's called residence time analysis. Residence time analysis has been around for a while. There are different methods. I'll show you one of the more common methods. So with residence time analysis, you put a grid of points on top of a map. And then when you calculate the trajectories, oops, oh, that's right. So suppose you calculate some trajectories. In this case, the trajectories are in Greenland. Rodolfo told you that I have a lot of projects in the Arctic. So I had a project where I was trying to determine the sources of the pollutants in the snow and the Greenland ice sheet. So here's an example of several trajectories. These are back trajectories that are programmed to arrive at summit, which is the top of the Greenland ice sheet. So the air goes like this. Okay, so we take the grid and we put it on top and we count the number of hours that the trajectories spend in each grid square. Okay, simple concept. So the results might look something like this. So we calculated trajectories, one per day for, I don't remember how many years, I think 15 years. And calculated the residence time. And what you see here is a plot of the residence time. This is the center of Greenland. Okay, and it's normalized residence time, which means we take the number of hours in each grid cell and we divide it by the total number of hours for all of the trajectories. Okay, so obviously the areas surrounding the center of Greenland has the most, because whenever the trajectories arrive, they have to pass through the same area. Okay? All right, so this represents the residence time, or the transport climatology, for every day for 15 years. This is the same, but only on the days that it snowed. Okay? So because we're interested for this project in determining the source regions for the contaminants in the snow. Okay, so the two patterns are very similar, but not exactly. It's a little bit difficult to analyze. So we created a difference field. So the one on the left minus the one on the right, right? So for every square in the grid. We take the residence time corresponding to snow days, and we subtract residence time corresponding to all the days. So we get a difference field or anomaly field. So the red values are positive. So this tells us that on the days that it snows, the air preferentially comes from this area, which includes eastern North America. And on the days that it does not snow, the air preferentially comes from these areas. So for example, Northern Europe, Scandinavia, even though they are closer, they are not frequent contributors to contaminants in Greenland snow. It's more the North Atlantic and Eastern North America. Now remember, and I keep saying this, remember the atmosphere is three-dimensional. So we can learn something more about these sources by considering the altitudes. So we have this grid where we count the residence time. So every time a trajectory passes through the grid, it passes at a certain altitude. So we record those altitudes. So what this shows is the average altitude, actually pressure, the average altitude that the trajectory takes when it passes through every region. So here, for example, Eastern North America, you remember that was one of the preferential regions to deliver air to Greenland when it snows. The colors here are red and orange. So 800, 900 millibars, that's close to the ground, within maybe 1 or 1.5 kilometers of the ground. So again, close enough to the ground to effectively transport contaminants to the ice sheet. Okay. So I've showed you two examples of how trajectories can be used in a climatological sense. Okay. Did I tell you that I like the Green Bay Packers? Did I say that? Okay. So now for the third part, I'm going to tell you about a recent study that we did with Rolando Olivas, who is a Mexican. He's from Nuevo León. This was his PhD project, working with me in Milwaukee. Okay, so this project was about developing an improved model for estimating concentrations of fine particulate material, PM 2.5. So I don't know if everybody here is air pollution people, so I'm going to tell you a little bit about PM 2.5. So here's, this is a hair, human hair, okay? These little particles here have an aerodynamic diameter of 10 micrometers, okay? And these very little particles here have an aerodynamic diameter of 2.5 micrometers. So PM 2.5 is particles of this size, very tiny. They can be inhaled. They can penetrate into the lungs. They can have negative effects on human health, especially for sensitive groups like babies and old people or people with respiratory problems. Okay. So in this project, we used some satellite measurements, I will explain what they are, along with a Lagrangian technique to improve the way that we can estimate concentrations. So there's an instrument called MODIS that's aboard 2 polar orbiting satellites. I don't remember the acronym. Do you know the acronym?
Moderate.
Okay. Yeah. Nobody remembers the acronym. Okay. So MODIS measures MODIS produces a product called aerosol optical depth. And what that is light attenuation, the reduction of light by aerosols, specifically by aerosols. Now, the reduction of light could be by absorption of light by the aerosols. It could be by scattering of light. They're both included in the aerosol optical depth product. So the larger values mean more attenuation, okay, more light reduction because of the aerosols. So in this particular day, here's the Great Lakes, North America. So the highest values are red. So this area here corresponds to forest fires in Canada. And this is a visible satellite image, also available from MODIS. You can see the forest fire plume here, okay, and also here. The winds, these are where the fires are. The winds are moving the plume over here. So you can see the higher values of optical depth here. Okay, so this is the product. Okay, so the state of the art for using aerosol optical depth measured by satellite to estimate PM 2.5, the fine particles, looks like this. It's a simple regression model. Okay, so you have some measurements of PM 2.5, maybe for a year, and then you also have the aerosol optical depth data from the satellite. You perform a simple regression model, you have an equation. So then maybe you have a day where the PM 2.5 instrument is not working, no problem. You can use the satellite measurement and this equation to estimate PM 2.5. That's how it works. It's very simple, and this is basically the state of the art, right? There are some problems with this method. Okay, one of the problems is that aerosol optical depth measurements can only be made during the day. Okay, so you cannot use this method at night. Another problem is that aerosol optical depth data is not available when it's cloudy, when there are clouds. And there are often clouds, more in some places of the world than others, more during some times of the year than others. And the third problem is that not all aerosols are the same. Okay, the thing that you are trying to predict, pronosticar, is aerosol concentrations near the ground. Most of the aerosols are near the ground, but not all of them. Some might be higher up in the atmosphere, and those contribute to the aerosol optical depth, yet they are not represented in this model. So this model, it's a nice idea, but there are some problems. Okay, so we had an idea that we can improve this model, this regression model for PM 2.5 by using what we call Lagrangian predictors. So the idea is this. If you measure aerosols here, usually those aerosols came from somewhere else. So they were scattering light or absorbing light somewhere else, upwind, maybe for 2 or 3 or 4 days before they arrived here. Okay, so the satellite should be able to see your aerosols now where they were yesterday. Okay, and also, as aerosols age, as they get older, their light attenuation properties change a little bit. So with this in mind, we added several terms to the regression equation. So this one with the 0, it means aerosol optical depth in situ, at the location where you want to know PM 2.5. This one represents 3 hours upwind. So using a trajectory, you can determine, a backward trajectory, you can determine where was this air 3 hours upwind. This is the aerosol optical depth at that location. Okay, and 6 hours upwind and 18 hours upwind, etc. Okay, so that's the improvement to the model that we proposed. Okay, so let me show you some things about the model. So here is the simple model, okay, the first model, the state of the art. You have observed aerosol concentrations, and these are the predicted ones based on the simple regression model using only aerosol optical depth in situ. And you can see that the model, this is the R squared, right, the square of the correlation coefficient, that it has some skill in reproducing the PM2.5 values, but not very much. So here is the same graph with the same set of observed PM2.5 measurements, but using the model, the multiple regression model, including the Lagrangian predictors. And you can see that the model improves a lot. So with the R squared of 0.5, that corresponds to a correlation coefficient of 0.7, which is not bad in the world of air pollution. Okay, now there are some problems with this method, some logistical problems. So this is the aerosol optical depth field for one particular day. You can, and it's the whole world here. So the coverage over the whole world is pretty good, but it's not perfect. There are some areas where there are no data, and that's because the satellite was on the other side of the Earth at the time. And there are other areas like here where there were clouds all day, so there are no measurements. So you have, with this model, you have a problem because you can only use aerosol optical depth when it's not cloudy. But that problem is multiplied because it has to not be cloudy at your location of interest. It has to also not be cloudy 3 hours upwind and 6 hours upwind, etc. So we have a problem with data availability. So let me just show you again another example of this. So here's, let's see, where are we? This is the Gulf of Mexico. Okay, so here's an aerosol optical depth field for one particular day. There's no data here because of these clouds. There's no data here because of these clouds. Okay, so this is a problem. So what we did is we decided to reproduce the data. In other words, in areas where there's clouds, how can we estimate what the aerosol optical depth would be if there were not clouds? So we did this analysis where we took pairs of locations and we sorted the pairs of locations by distance, and we determined how well the aerosol optical depth here was correlated with the aerosol optical depth here as a function of the separation of the 2 points. So here you have the correlation coefficient, and here you have the distance. So what we see is when the distance is 0, the correlation is perfect, okay? But as the distance increases, the correlation dropped. So we chose a distance of 100 kilometers. At 100 kilometers, 2 locations are correlated with the correlation coefficient of 0.5. Okay, not bad. Now, you could argue about maybe we should have used 50 kilometers or maybe we should have used 200 kilometers. It doesn't really matter because what we did is we estimated the aerosol optical depth in the cloudy areas using a distance-weighted interpolation technique. So the weights is 1 over distance squared. Okay, so the larger the distance, the smaller the weight, so the choice of 100 kilometers really doesn't matter. So using this method, we can reproduce. We can reduce the problem of missing data. So here is a aerosol optical depth field for one particular day. You see all the areas with missing data because of clouds. Once we fill in the gaps, it looks like this. Okay? Now, the original, You have some features like a forest fire. I think this was the same picture that I showed you before. Forest fire, plume from the forest fire. You have some cities. Here's Los Angeles here. Some cities with more particulates, more pollution. Okay, we interpolate, and the principal features are maintained. Los Angeles. Okay, but there are fewer gaps without data, only a few. Okay, so we did this every day for 5 years. We created this gridded product, and this is what we use to evaluate our multiple regression model with the Lagrangian predictors. So here's side by side, original and reconstructed. Okay, so let me show you the results. So we chose 10 sites in the United States, a 5-year period from 2003 to 2007. We used one measurement every day. Okay, so here is the results for the simple regression model, right? Only one, that AOD 0. Okay, 200 samples. Now, why 200 samples? 5 years has a lot more than 200 days, right? Well, even with this method of estimating the AOD in cloudy areas, there are still a lot of areas that don't have data. Okay, so it reduces the sample size tremendously. Okay, so this is the R-squared value, the square of the correlation coefficient. So with the simple model, it's not very good. The median R-squared value is less than 0.1. Not a very good model. When we use the multiple model with the Lagrangian predictors, the model skill improves tremendously. Okay, it's still not that good. We need to improve it more. This is a control that we used, and in our case, the control is we used the model with the Lagrangian predictors, but the Lagrangian predictors corresponded to random locations. That was our control. Okay. So these results were for all year. So here we have results by season. And we see that the model performance in every season, you have the simple model, the new model, and the control. So we see that the results are different in different seasons. So that gave us the idea to include some more predictors in the equation that identified the season. So we did that. So we did it in 2 ways. We included the seasonal predictors in the simple model with only one AOD value, and we also included them in the multiple model with many AOD values. So these are the new variables, CAT. Okay, they are seasonal categorical variables. They have a value of 1 or 0, depending on the season. And what we find is, let's see, oh, sorry. So here was our simple model that you saw before. Here's the multiple model that you saw before, represents an improvement. Here is the simple model, including the categorical variables. So that is provides a lot of improvement compared to the regular state-of-the-art model. And in fact, surprisingly, well, I was surprised, it actually provides more improvement than using the Lagrangian predictors. Now, the Lagrangian predictors also improves this model. So the best is a model with the Lagrangian predictors and the seasonal variables. So for all of our data, we were able to improve the median R-squared value from less than 0.1 to 0.3, a factor of 4 improvement. We thought that was pretty good. Okay, so a correlation an R-squared value of 0.3 corresponds to a correlation coefficient between 0.5 and 0.6. Okay. Here are the results of the multiple plus seasons model for our individual sites. So you can see that the performance, the model performance is different from place to place. In Milwaukee, it's the best because it's Milwaukee. But it varies, and probably the reason for this has to do with where the aerosols are generated. I mean, the whole idea of including the Lagrangian predictors is to include the optical effects of aerosols as they age. Okay, if you're in a polluted place, most of the aerosols in the atmosphere are very young. They were generated right there. So the aging doesn't add as much, and that might be the reason why some of the other models don't perform as well. Okay, so the conclusions I have for this final part of the talk, the PM 2.5, is that the Lagrangian variables, they improve the model. Seasonal variables also improve the model, and of course you put the two together, you get the best improvement. So finally, I want to thank my friends at CCI, especially Rodolfo Sosa, for inviting me, and I hope this was interesting for you to see sort of an overview of Lagrangian models and what you can do with them and how they can be used in air pollution studies. And I'd be happy to answer any questions.
Thanks, John. Thank you very much. Vamos a iniciar la sesión de preguntas. Les voy a pedir, por favor, dan su nombre y la institución o grupo al que pertenecen. Yo conozco prácticamente a todos los que están aquí, sin embargo, el doctor Kahl no. Y darle la información, o sea, que se identifiquen, pues le va a permitir percatarse de la diversidad tanto de académicos, de estudiantes y de instituciones que están aquí involucradas e interesadas en su tema. Que si van levantando su mano, por favor. Adelante. El doctor Kahl entiende español, si alguno de ustedes quiera hacerla de esa manera. También tenemos una excelente traducción simultánea y las personas, por supuesto, que quieran hacerlas en inglés con mucho gusto. Adelante.
Thank you very much, Doctor. Muchas gracias. My name is Demian. I study geography, and I am from the Faculty of Philosophy and Letters from UNAM. I have a question. What kind of mathematics do the meteorologists use?
Well, in our program, we are very heavy in mathematics because we are part of a mathematical sciences department. Typically, students studying mathematics at the undergraduate licenciatura level, they need 2 semesters of calculus and differential equations and maybe numerical methods. For us, we have requirements of 4 semesters of calculus, including differential equations and vector calculus. I think our requirements with mathematics are heavier because we are part of a mathematics department.
And I have another question, is the last. In the presentation, you put the high pressure and the low pressure at the beginning on your presentation. You talked about the wind. The wind only occur at the low pressure, or it can occur at the high pressure?
No, there's wind everywhere. And the point of that slide is that if you calculate your trajectories in an area where the wind is very homogeneous and it doesn't change much over the space, then all of the trajectories in your grid will look the same, and then you have the better confidence Okay, if it's in an area where with heterogeneous winds, then they will diverge, and that can happen in a high-pressure system or a low-pressure system.
Muy bien. ¿Alguna otra persona, por favor?
Thank you. Thank you for your talk. It was very interesting. I miss the argument where you conclude that the trajectories were more frequent in Greenland when there was snow than when there was not. How was that? Sorry.
Okay, so every day for 15 years, we have a trajectory that arrives in Greenland. Okay, so we pass that through this grid, and we count the number of hours, okay, that the trajectories spend in every part of the grid.
Okay.
And then we normalize that. Okay, we divide the number of hours in every grid cell by the total. Okay, so, and then we take that field only for the days that it snows, and we subtract from that the field for every day.
Okay. I thought you were relating that with the time residence.
Yes, yes. The grid, the values that we are using is the residence time. So what that tells you is that the residence time in certain areas is larger on the days that it snows.
Yeah, I can get it. Yeah.
Okay, so that means that when it snows, the air comes from those places.
Okay.
¿Alguna otra pregunta, por favor?
Thank you. My name is Alejandro. I come from SEDEMA, from Environmental Agency. My question is about the clouds. When we try to adjust a model, any model, we shouldn't use images with clouds. But if I have two images, there's no problem. But if I had 1,000 of images, how can we remove that clouds or that days with clouds?
Well, that's a difficult question. It depends on the application. Clouds exist. They're a very important part of meteorology and of climate. In the case of aerosol optical depth, in that case, clouds don't really matter. Okay, some source area can contribute pollutants to another area if there's clouds or if there's no clouds. So for that reason, we had no problem removing the clouds. Okay, but if you are doing something else like a meteorological model, you can't remove the clouds because the clouds are part of the system. So without knowing more specifics, it's hard to answer your question.
In relation to PM25 estimation.
Yeah, well, if you use aerosol optical depth, then the clouds, in a certain sense, the clouds don't really matter. So you can remove them, but it's difficult to remove them. We created one method for removing, well, not completely, but for reducing the missing data areas. So that's one suggestion. You could use a method like that.
Okay. Another question: if I want to compare the estimation in an image or the result image, the result grid, I have also monitoring station in the ground, but there's only one point. Could we adjust a statistical model to compare images from, or the method for remote sensing at that geostatistical method?
Yes, you can, but it's difficult. It's like verifying precipitation forecasts from meteorological models. The precipitation forecasts, by definition, are area forecasts, area of the grid cell, and your observations are point measurements. So With one observation, it's very difficult. You can compare one pixel of your images to that point measurement. If you have more point measurements, then you can use some spatial smoothing technique like kriging or something like that to create a spatial field. But again, it depends on how much measuring locations you have.
Okay, thank you.
¿Alguna otra pregunta? Gracias.
Thank you very much.
Bueno,
Thank you. My name is Ruben. I'm from the PhD student from the spectroscopy and remote sensing here at UNAM. My question is, if I understood correctly, your equation for AOD accounts for the location of aerosols depending on their, well, based on the trajectory model. But could you also account for the pressure? Because as you said, it's different if the parcel comes from a 100 hectopascal level or from ground.
Well, we know the pressure because the trajectories are three-dimensional and we know the vertical coordinate at every point. But in this case, for this application, the pressure doesn't matter because the AOD measurement is a column integrated measurement. It measures light attenuation by aerosols over the entire atmospheric column.
But the final result, or the quantity you want to quantify is the concentration, right? PM 2.5.
Yes.
So is it only? So that's the concentration in the whole column?
No. Yeah, the thing we're trying to predict is the concentration close to the ground. But that is almost the same as the concentration in the whole column, because most of the aerosols are close to the ground.
Okay. Thank you very much.
Hi, Graciela Raga here from CCA. We were talking earlier about the effect of relative humidity on the aerosol optical depth, but more than that, I was just thinking that the trajectory, the Lagrangian predictor, you can also put something like the precipitation along the trajectory, not only so even though you might have a trajectory that goes over a source, if there is precipitation between the large source and your receptor site, then a lot of it would have been scavenged. So perhaps we could also refine some more, putting some other predictors, like precipitation along not only the category of the season.
Yes, that's a good idea. We thought about including meteorological variables in the regression, but in situ, not upwind. But that's a good idea. For example, Lagrangian relative humidity. High split, which is the trajectory model that most people seem to use, that has an option for outputs of relative humidity and up. Yeah, right. So that would be interesting to try.